Hi, today I'm going to start talking about acids and bases. And before we do, get out your reference tables. You're going to look at table KL today, K and L. And eventually we're going to move on to table M. We're going to introduce a new vocabulary word. We have the arrhenius theory. And the arrhenius theory describes basically the behavior of acids and bases. And it has to do with positive ions. So in an arrhenius acid, the only positive ion is the hydrogen ion, which is also, coincidentally, this is also the word or the symbol for a proton. Think about this. Hydrogen. This is the notation for it. This number refers to the protons. And this refers to the atomic mass, which is really protons plus neutrons. So when I subtract from the mass, if I subtract the protons, I'm going to get the number of neutrons. So if you do 1 minus 1, you actually have 0 neutrons. And hydrogen has no neutrons. So when you have an H+, it actually, like you learned in the last unit, lost an electron. So it just went from being 1 proton and 1 electron to being 1 proton. Again, this has 1 proton and 1 electron because it's neutral. This one has 1 fewer electron, so it's just a proton. Okay? A little bit of review. But an arrhenius acid has only a proton as the positive ion in solution. What does that mean? So when we look at table K, you're going to see you have acids like hydrochloric acid, you have nitric acid, sulfuric. So HCl, and it has to be written as AQ because it's going to dissociate. These are all electrolytes. They will conduct electricity, but they will also dissociate, meaning they'll split up into their ions. So HCl is going to break apart into H+, aqueous, and Cl minus, aqueous. Now, because this is the only positive ion in solution, in other words, H+ is it. This is an arrhenius acid. What's an example of something that is not an arrhenius acid? Well, I'll look at NaHCO3. When I get out my reference table E, I'm going to notice that HCO3 is in there. It's actually hydrogen carbonate. So this is sodium hydrogen carbonate. This is going to break apart into sodium ions and hydrogen carbonate ions. This is a positive ion. It's not hydrogen. This is not an arrhenius acid. Okay? Now, let's look at the other side, an arrhenius base. So an arrhenius base is any compound that breaks apart leaving hydroxide as the only negative ion. So hydroxide is the only negative. How do you name hydroxide? Well, you look in table E. It is right here, middle on the right side. Now, an example of arrhenius bases, in fact, if you look at table L has 4 bases, 3 of them are arrhenius bases. And I'm going to show you sodium hydroxide and ammonium. So I'm going to write AQ to show that they're both dissolved in water. Now, when these break apart, I'm going to get sodium ions in solution. And I'm going to get hydroxide ions in solution. And these hydroxide ions, because it's the only negative ion, that makes this an arrhenius base. Now, ammonium is also a base, however, it's not an arrhenius base, according to the arrhenius theory. It's actually a base according to the Bronsted-Lowry theory. I'll write that here. You don't need to know this for the reagents. I've never seen it on the reagents, a student having to tell the name of it. But you just have to know that it's another theory, and all it really means, instead of the hydroxide being the only negative, it is a proton acceptor. Okay, so what does that mean? Well, I'll show you. It means that if we start out with NH3 and we add a proton, we will get NH4 plus. So this is showing that it is a base, it is a proton acceptor. It's adding another H. So if it goes from having 3 H's or even 2 H's to a higher number of H's and nothing else changes, that's a proton acceptor. So as long as you're increasing the number of hydrogens, you can call it a Bronsted-Lowry base instead of an arrhenius base. Okay? That is why ammonia is a Bronsted-Lowry base. You don't need to know the name. Remember that. Okay. Now, there are going to be some practice problems that I want you to try out. Peace.